I'd just like to say real quick, we have a really great list of 4 speakers, and so they'll have 30-minute talks each. And the first one is Stan Osher. And I'd like to really thank the last group of speakers. We've tried to put particularly good speakers at the end to keep people here, and there's still a pretty good turnout, so thank you.
Okay, it's nice to be here at this place, which has developed tremendously in the last couple of years. The people here are terrific scientists, and they're nice, which is almost a contradiction in term. And one of the nicest is sitting over there, who is most brilliant, is, of course, Ingrid, and I'm actually going to talk about wavelets, which is amazing. So watch carefully. Okay. So I'm talking about compressed modes for variational problems in math and physics with these 3 guys from UCLA. The first person is a physicist, and he came to me with a really good idea, which turns out to be not totally original, but still very, very sensible. Namely, sparsity in a continuous setting dealing with functions should have something to do with compact support, which I thought was a terrific idea, and you'll see that it actually works. So I got into information science using PDE. I went back, I started from solving flow past an airplane with shock waves and God knows what all, and that led to total variation and image processing. Now we're going backwards. The tools in information science will be useful in solving scientific computing problems, I think. So here we go. Okay, let me press down. So we all know, this I can skip, this is for general audiences, L1 is good, right? Okay, not just good, it's great. And sparsity is typically, at least in my mind, was typically associated with discrete objects rather than a continuum. So what's an analog of sparsity to continuous functions? And how do you construct continuous functions which have compact support and which satisfy certain properties? And the answer to all questions is L1, including this one. So let's see how this works. This all started, this physicist friend of ours, Vidvid Oslins, who's a really smart guy, told us about one-year functions. So some of you know about this stuff. I just heard about it a few months ago. If you think about Laplace's equation, and you add a potential, and look at the eigenfunctions of this operator, typically, they are not sparse. For example, if the potential is 0, the functions are sines and cosines and whatnot, and they have support all over the place, right? And physicists don't like that. What they wanted to do was replace the eigenfunctions of this operator of theirs by functions which are 0 a lot, and decay. In fact, they would like them to actually be 0 outside of some set, but they weren't able quite to do that. So one-year functions were introduced about 60 years ago, I think. And what they did was take linear combinations of the eigenfunctions of the Schrodinger operator, which means Laplace, that's Laplacian over there. If you're an engineer, Larry tells me it should be written as del squared, which is what I used to do, but I've been around mathematicians for a long time. And what they did was take the eigenfunctions and basically rotate coordinates in such a way, take a whole bunch of them, the first 10 or something, and try to take linear combinations so the result you got was 0 at infinity for most of for the functions. And that's become a little industry, cottage industry, and we're going to do something which is much more systematic, but it's inspired by their stuff. So what they did, as I said, is they took this operator H, which is Laplace minus Laplacian plus V, and they found the eigenfunctions by using this variational problem principle, which is Rayleigh-Ritz method or something. And then they rotated coordinates to try to sparsify these things, okay? So what we're going to do is much more systematic. And arrogantly speaking, it works much better. It gives you lots of freedom, but we don't get exact eigenfunctions. You'll see what we get, but we're pretty close. So what we're going to do is get a variational method that does what one-year wants to do. So we're going to do this for a special case first and to show some pictures, then we'll talk about how it works, and we'll even have a multi-resolution way of doing it. Okay. So there's something called the 1D Kronig-Penning model. So one more time, we are looking at minus Laplacian of u plus v times u with some boundary conditions. And now what we want to do is expand in terms of some functions, but we want the functions not to be the exact eigenfunctions, but things which have compact support and are close to the exact eigenfunctions. And there's a lot of reasons why you want that. It sparsifies things. If you have to do an S3D or something, not too many functions get involved. You can also, and also physicists like local interactions. They believe things are local, and they are. Okay. So here we go. The 1D chronic penny model. I don't know much about this, so I'm just reading what I've been told. You take a 1D lattice of positive ions, and the potential V looks like that. It's a bunch of dips. Okay, so we're taking Laplacian of U plus V times, minus Laplacian U plus V times U. V looks like that. And that's approximated by something called the chronic penny model, where they replace those curvy spikes by this dip. And the reason they do that, I think, is because it's easy to sort of solve this problem analytically. You get sines and cosines in various places, constant coefficient with jumps. So they can get a handle on it. Anyway, that's the potential that they use. It's an array of rectangular potential barriers. Okay? And these are the first 10 eigenfunctions. There are 10 colors here. I'm pretty colorblind, but people tell me there are 10 colors here. 10 different functions, and they're all global. They're all global. Okay? Those are the true eigenfunctions. And then we do our super duper trick. No, sorry, not yet. This is this initial input. And down below, these are what we get doing what I'm going to tell you about in a minute. Each of these 10 functions has compact support with some overlap with its neighbor. They are orthonormal. And they are approximate eigenfunctions of the original operator. But their support is extremely local. So how do you get these things? And, well, you get them unsurprisingly as follows. Well, first I'll show you the results. I mean, if you look at the span of the first 10 eigenfunctions between the approximate and the ones we have, this graph is supposed to tell you they're right on the money. So the dots are in the middle of the circle, as they should be. So these functions, top and bottom, have the same linear span, but the ones on the bottom have a compact support. And the ones on top are exact eigenfunctions. The ones on the bottom are close to being eigenfunctions. And how close? Okay. So that's the punchline of this stuff. So how do you do all this? Well, if you want, let H be the operator that we are, this symmetric operator that is elliptic and has this potential V. And what you do is minimize not just psi inner product H psi such that the norm is 1, but you add what else? Mu times the integral of psi. That's all you do, absolute value. That's all you do. So you solve that optimization problem. And that's what we did before. Of course, we're going to get more. This gives you the first eigenfunction. Repeating this, you can get the first n, however, as many as you want. And it's kind of cute to see what happens. If you look at the Euler-Lagrange equation you get, it's this thing H C1 plus mu sine C1 equals lambda C1. If mu was 0, we would have essentially, and V was 0, for example, we would have Laplacian C is equal to lambda C. But we don't have that. We have Laplacian C plus mu times the signum, if you allow me to call the subgradient signum, it's not exactly signum, equals lambda. So if you look at that thing and you have a strong enough stomach, it's not very hard to figure out what happens. The first eigenfunction is something which looks like a peak. I should have a graph, but I don't. The width of that peak, that number L, goes to 0 as mu gets larger. Yeah. The bigger the mu, the sparser it is, and the more you get like a delta function. When mu goes to 0, you get the original eigenfunctions. But for moderate size mu, you get things that approximate the correct span of the operator. So this is the first part of the talk. This is the main point. Any questions about that? Okay. That's the deal. Okay. And you can do it recursively. You do the same thing. Well, you do the same thing, but you make psi orthogonal to the first k minus 1. And we call these compressed modes of the Schrodinger operator. And how do you actually compute them? Well, you can do them all at once. And this is, for that we use a super-duper split Bregman with a constraint that you lie on this Stiefel manifold, which is this fancy way of saying that C transpose C is the identity. So we basically do that minimization for n eigenfunctions, the first n, subject to the constraint that psi transpose psi is the identity, and that makes it into a non-convex problem, but not terribly non-convex. So if you're interested in the numerics of it, it's just split Bregman, which in real life is ADMM. And in the middle of the splitting, you do an exact projection onto the manifold psi transpose psi equals I. And as always with L1 and split Bregman or ADMM, it converges very fast. So this is not terribly much slower than just solving the problem without having the mu there. So for a little bit of extra work, you get these sparse functions. And I'll skip the details of split Bregman and the history and all that jazz. But the bottom line is there's the algorithm, which is not a big deal. Many of you have programmed something like it for other problems. Okay? So that's the deal. There's one non-trivial step, which is the projection onto that manifold, and that involves an SVD, which you would need even if you were doing the case without mu. It has to be there. And the nice thing about our SVD as opposed to old SVD is the functions involved are sparse. So the inner products are not complicated to or not expensive to evaluate. So that's the method. And these are the results for the free electron model means V equals 0, which means just Laplacian, which means sines and cosines or whatever they are. So we are replacing sines and cosines by these local guys, amazingly enough. And they span almost the same space as, if you take enough of them, the same number of the first n eigenfunctions, the true eigenfunctions, compare them to the first n approximate eigenfunctions. And for a relatively small n, the results are pretty close. Okay. This is the chronic Penny model where you have, it's easier because you have real potential, which sort of makes things more local more easily. And they are very close indeed. These are what you get for the first 10 eigenfunctions. This is what happens in 2D, which is very doable, which we really haven't investigated yet in detail. I must have gone backwards. Yes, I did. Okay, and these are the comparisons. The eigenvalue comparisons stop midway. If you go too far out, they start diverging, unsurprisingly. If you go all the way out, they're right on the money because at that point, everything is an eigenfunction. You can just take delta functions. But in the middle, which is the interesting part, they're very close. So one more time, the point is to span the same eigenspace as spanned by a dense set of functions which arise in physics by functions which have compact support. And we use L1 to impose sparsity. The closest thing that exists in information science seems to be sparse PCA, which I found out about after we did this, but it's different. First of all, there's no PD involved. However, they are looking for sparsity of eigenfunctions. But they also try to diagonalize things, which is not what you want to do here. So this is different. This is different. Okay. And now what we're going to do is make a multi-resolution version of this, would you believe? We're going to create things that look like wavelets and which are approximate eigenfunctions of the Laplacian. We could make things with approximate eigenfunctions of more complicated operators, but the Laplacian without V allows you to take Fourier transforms. Constant coefficients, so it's a really, 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 really easy computation. So here's the deal. Just for the Laplacian, You take, as usual, a basis in d dimensions, you take j omega, and you look at, and the operative condition is over there. I haven't got a pointer, but you can see it. Inner product of c with c of x minus j w is delta j0, period. And we call these things basic compressed plane waves. So we're going to minimize grad u squared, which gives it a Laplacian, plus mu times the integral of u, absolute value, such that these constraints are satisfied. These orthonormal constraints are satisfied. And this turns out to be easy to do because of Fourier transform. So implementation is easy. Okay. And I'll skip the details. And this gives you level 1 of this so-called multi-resolution decomposition. I'll skip, again, there's some technical details that are very simple, but it's all linear because of that, because of Fourier transform, so every step is easy to evaluate. It's almost the same as the previous algorithm, except for this crazy condition about C being orthogonal to its translates. Okay? And this is what they look like. They have a nice wavelet feel, sort of. This is level 0, level 1, and so on. And they look nice. I like them. And again, these things come from from solving Laplacian u equals lambda u almost, plus signum of u times a constant, and plus this orthogonality constraint. So these are almost eigenvalues of the Laplacian. Not quite, but close. Okay. So you can fit these guys in an interval. I'm moving along. These are 20 of the first 4 of these basic compressed, what do we call them again? Plane waves. And if you look at the spectral density distribution, it looks nice. It gives you a nice adaptive way of approximating things like the piecewise constants. And there is a nice transformation that allows you to compute these coefficients. So you can expand in terms of these guys pretty easily by using Fourier transform. I won't go through the details. But there's a simple transformation that does it. So we use that for that chronic penny model when we took a potential which had a very deep dip, and we got the eigenfunction, which looks like this. I mean, these are the basis functions. And you can do a windowed version of this where you realize where the singularity, where the action is, and just do it locally. There's also an inverse transformation from F in real space to frequency space, which is rather simple. Again, easily just Fourier transforms. And this is the second lowest energy state of the that chronic penny model for that special potential. And I think it's my last slide, amazingly enough. So the conclusion is we propose a variational method to create compressed modes as an analog of sparsity continuous functions. We have a numerical method which is almost as fast as if there were no sparsity requirement. The expensive part is the SVD. We have a method for solving the non-convex problem, which we had before. And we also get localized orthonormal basis. And we want to extend this to other problems which have a similar structure, which arise in physics. And that's probably it. And happy birthday, Ingrid. Okay. Yep. Yes.
Do you also have downsampling operators?
Sorry?
Do you have downsampling operators at the difference case?
I'm not sure what that means, but we.
Wavelets when you go from scale to scale, you downsample because you go to lower and lower frequencies, for example, so you can downsample the space.
I haven't thought about it, but that's a good question. But we get, we get these we get C sub n, which is like 2 to the k or 2 to the n by orthogonality. So.
But they're essentially band limited, and so you would expect that you need fewer samples.
Yeah, we should look about that. Okay.
More questions? Let's back stand.
Okay.